Hello everyone, my name is Kit Boyett and I am a third year PhD student at the University of Oxford. And this is a talk about a paper I will be submitting over the summer. I would hope that you keep your eyes and ears open for when it is released later this year. And as this is just a quick talk, I'm going to focus on just one aspect of this paper, and that is the evolution of the extreme emission line galaxy abundance between a redshift of 2 and a redshift of 7. And this work is done with a whole host of people who are listed at the bottom of this slide. So to start, I am going to begin with a bit of theory to motivate this work. I'm looking at the epoch of reionisation. And here's a classic figure of the evolution of a neutral fraction of hydrogen with redshift. It's one from Robertson et al. 2015. And here the black points tell us constraints on when and how quickly reionisation occurred. And these come from looking at the cosmic microwave background, from looking at the absorption seen in the QSO spectra at high redshift, from looking at the visibility of Lyran alpha emission. We can also say about the epoch of reionisation is that the main ionising sources are stars forming within galaxies, as opposed to, say, from AGN. So in this work and in this talk, I'm going to be considering the galaxies that are analogues of these star-forming galaxies, but at lower redshifts. One of the things we can say about the constraints from reionisation is that galaxies must show some level of evolution between what we see locally at low redshifts and the galaxies existing during the epoch of reionisation. At higher redshifts, galaxies need to be better ionizers to match those constraints. And so this would require galaxies to have larger escape fractions, this being the amount of ionizing radiation is able to escape from the galaxy. Galaxies would be required to have larger ionization efficiencies. This means that galaxies of given UV luminosity needs to be producing more ionizing photons. And we're already seeing glimpses of these conditions, that galaxies at high redshifts are better ionizers from such observations as strong carbon emission from high ionization species such as C3 and C4, seen above redshift 7 here, or from strong O3 plus H beta emission, such as that's seen here from Smith et al. 2015, where we have seen emission equivalent whips in excess of 2,000 angstroms. Now, at low redshifts, we do have analogues of these galaxies, and these are extreme emission line galaxies, so called because they exhibit, well, extreme emission. They show very large O3 equivalent whips, and we tie this to the upturns in their star formation rate. So as to whether these analogues, these extreme emission line galaxies, are actually ideal ionizers, ones we're looking for, I refer you to Tang et al. 2019, who built a sample of these extreme emission line galaxies where their O3 5007 equivalent whip spans a large range, and they found, so redshift 2, by the way, that the equivalent width trends with the O32 ionization parameter. Now this is important because it has been seen that large escape fractions are only found in galaxies that exhibit large O32 values. So large O32 is a necessity, but in itself is not sufficient for a large escape fraction. And that is shown in this plot here by Nakajima et al. 2019 on the right-hand side. And I've shaded in grey the region above an O32 value of about 6. And this is where you gain such large, or the potential for such large escape fractions. A value of 6 roughly corresponds to an equivalent width in the O3 line of about 700 to 800 angstroms. So keep that number in mind. Next is that Tang et al. Also found that the equivalent width also trends with the ionization efficiency of a galaxy. So for example, if you had a galaxy which has an extreme emission line in the O3 greater than, say, 750 angstroms, then not only does it have a higher ionization efficiency than typical galaxies at low redshift, but also has the potential for larger escape fractions. And if you're wondering why this is, well, it's the fact that the conditions that promote large O3 equivalent whips are the same conditions that promote ideal ionizers. And we're considering here, young, bursty systems, potentially at lower metallicity. The younger systems have fainter optical continuum, allowing larger optical equivalent whips to be measured. The hotter massive stars, metal poor stars, providing stronger O3 emission. Together, those two provide are very strong equivalent widths. But for the ideal ionizers, the younger stars provide the harder ionizing spectrum, a larger ionization parameter. And if they are bursty, such as figure A in this plot from Jaska et al. 2019, if they're bursty, then you have the potential to build this sort of like picket fence structure where light continuum may escape through sort of different pathways. And so galaxies which have large O3 equivalent widths are seen as ideal ionizers. The next question is, how common are they? And so this is what I've been focusing on in my work. So I want to ask the question, how rare are extreme emission line galaxies at redshift of 2? And to do this, I utilize recent HDUV photometry over the Goods North and South fields. I use their photometric redshifts to build a UV bright sample of about 900 galaxies, being redshift of 1.7 and 2.4. And this says that the O3 emission line should fall within the G141 GRISM and be available to us through the publicly accessible 3D HST slitless spectroscopy dataset. One example of a spectra is seen here on the right-hand side. So we use this GRISM emission line flux, and we use the photometry together to constrain the equivalent widths of the O3 5007 line for all these galaxies. And then we model this using a log normal distribution. And that brings us to the main result of our work, and this is the O3 5007 equivalent width distribution at redshift of 2. And I've shaded in a big blue box those galaxies which have a equivalent width above about 750 angstroms. These are our ideal ionizers, the ones with the potential for larger escape fractions and have higher ionization efficiencies. And they only make up about 2% of our population based on our best fit model. And this stands in very stark contrast to what's being found at higher redshifts, such as at redshift 7 here by Ensley et al. 2020. Now in their work, they use EWASS excess to observe the O3 plus H beta emission above redshift of 6. And again, on the right-hand figure here, they model their distribution as a log normal. And again, I've put a box to sort of describe where you'd find these like ideal ionizers. And you can already see that this is going to cover a much greater portion of the population than just 2%, like we found at redshift of 2. Perhaps a easier way to explain this or to visualize this is to show how the EELG fraction changes with redshift. And this is the fraction of galaxies within a population that exhibit an equivalent width in their O3 5007 line above some given threshold, above 500 angstroms, above 750, above 1000, and see how that changes with redshift. And I compare my results in blue to results through EWASS excess at higher redshifts. And we see that that fraction increases. Galaxies at higher redshifts, a greater proportion of them show larger equivalent widths. And we put this down to an increasing specific star formation rate and a decreasing metallicity towards the epoch of reionization. And again, to take us back once more to the ideal ionizers, which they have a equivalent width of 750, that equates to about 2% at redshift 2, but about 25%, sorry, at about redshift of the epoch of reionization. And again, this is important because these are the galaxies that are meeting the conditions for, the potential for large escape fractions, high ionization efficiencies. And lastly, I'll remind you that this also sort of is telling us perhaps that a greater proportion of galaxies are exhibiting this bursty star formation seen in, say, figure A here, at these higher redshift epochs. So that's that. I think it's going to be a quite quick talk. Basically, EELGs do present ideal ionizers at moderate redshifts. They have larger ionization efficiencies and they have the potential for larger escape fractions, especially when they have an equivalent width above, say, 750 angstroms. And though they're rare at redshift 2, their abundance increases with redshift, which we put down to the increasing specific star formation rate or a decreasing metallicity towards the epoch of reionization. And once more, I'll be submitting this work over the summer, so do please keep your eyes and ears open for that. Thank you very much for listening. Hope you have a good conference.